We're going to start from Edge Impulse on EON Tuner. So the speaker is going to be John Jung from Edge Impulse. He's been working on TinyML for 3 years, but it feels like a decade now, I guess, Jan, right?
Very true.
First, he started as a principal engineer at ARM, and now he's the CTO and co-founder of Edge Impulse, which is actually flying high these days. And they've shipped, he has shipped devices, work on latest network stacks, climb up on buildings. There is a monument in San Francisco with his name on it. So I'm actually quite interested in the presentation, but I'm quite puzzled with the monument. Maybe you can start with the monument, Jan.
Thank you, Evgeny. Yeah, so when Mozilla turned 20 years, they put a monument in San Francisco with all the names of the contributors to the Firefox code base. And I worked for 2 years on Gecko, the render engine that powered Firefox and Firefox OS. So if you're ever near there, it's a brilliant little thing. It has the Firefox logo on it, and the names of a few thousand amazing people.
That's good to know, Jan. What is going to be your next monument?
Let's see. I mean, after this presentation, maybe someone wants to raise one for us.
Oh, yeah, go ahead.
Thanks, Evgeny. Yeah, so my name is John Jung. I am the co-founder and CTO of Edge Impulse, as Evgeny said. Edge Impulse, we actually launched it sort of kind of a week before at the TinyML Summit last year in California, early 2020. It's been an amazing journey. It's kind of a product that I always wanted to exist for TinyML. I am not an ML engineer, and I'm an embedded developer, and I see kind of the power of where machine learning can help me write better control loops. It can assist me writing this kind of thing. But it was really hard for me to get started in this ML journey. Like, how do you collect data, all the stuff that Eilat just talked about at EMSA. How do you kind of design this pipeline, and where does finally the ML, the deployment part, fit in? So we founded Edge Impulse as the place from engineers for engineers every step of the way, from your initial data collection all the way to deployment. It's been also, thanks to the amazing TinyML community, a fantastic success. Over the last year and a half, we've grown from 0 to 26,000 real ML projects. We're deployed in electricity grids, conservation projects, asset tracking, sensors around sheep necks, etc., all around. And one of the things that I realized very early on, and it's just because I'm not an ML engineer and I just don't understand kind of the underlying technique so well as a lot of the researchers in this community, is that signal processing is the ultimate companion of TinyML. And that's cool, because let's take a look here at this super noisy signal, right? This is data from an accelerometer. I think I'm just, waving an accelerometer around. If I need a machine learning algorithm to figure out exactly kind of what is happening here, and classify whether that's normal data and what that class of data is, then I might need a machine learning to learn kind of to denoise this algorithm first. It's kind of stupid. We already have all kinds of techniques in our signal processing toolbox that we've been using for the last 30 years to write intelligent devices. We just call it signal processing rather than ML. So I have this, really noisy graph. I apply a low-pass filter, bam. Now I have, this is the exact same signal, but after, small low-pass filter at 3 Hertz. And now I have a really clean data set. Much easier for me to do something, much easier for the ML algorithm to do its job, whether it's a neural network or a classical ML algorithm. So a lot of the stuff that we do, at least, and I think that is kind of front and center in all the places, or all the companies that apply TinyML for real solutions, is that they heavily leverage signal processing. And in a way, kind of what EMSA said, where they have kind of a small classical ML thingy in front of it, kind of feels in the same way, right? You have something you understand really, really well, and you use that as kind of a first pass, maybe to denoise or to find like this first bounding box. And then finally, you're running kind of the magic, the neural network at the end, to then do the real classification. So we see that in lots of places. So this significantly reduces the number of input features. We can't run object detection on an MCU. We can't analyze a complete waveform, 16,000 points on an MCU. But if we just reduce these input features, denoise it already, we can have much smaller algorithms, much smaller networks that do their job much better, which is really cool. So if you look at kind of a typical sensor pipeline, this is for everyone who's ever worked through one of the examples in the TinyML book by Pete and Dan, or has ever looked at kind of how to do wake word detection using TinyML. You realize you have an input signal. There's a bunch of variation that you can do with that, but then there's a processing step, for example, creating a spectrogram, and then finally we feed that spectrogram into the neural network. That's kind of our typical ML sensor pipeline for time series data. Now, how do you know what the right parameters of these things are? For the neural network, there's this kind of whole flow around AutoML research where people say, well, we have a sort of an idea of kind of the number of layers that we want in this network, but we don't know, how many convolutional layers do we want here? How many dropouts should I use? What should the learning rate of this algorithm be? That's kind of the parameters that you can play with. So there's been a whole bunch of amazing tools where you just say, here's my algorithm, or kind of my base neural network architecture. Go figure out what gives me the best results. AutoML. Now, that is cool and it works, but if you look at kind of this whole pipeline, it's only a very small portion of that pipeline where this research is happening. And what we've realized is that the quality of the data that feeds into the neural network is much more important than what happens in the neural network itself. What are the parameters that go into the spectrogram here? What do I do with the speech signal before I actually pass it in? So for us, this whole part is a much more interesting kind of target of AutoML. I would call it more assisted ML. AutoML sounds a bit too magical. So this gives us a wide range of parameters. So some examples. This is from a real data set actually in our platform. Whether someone hears a titmouse, yes or no. So we have kind of the tweets of what the titmouse does, and we have a long sample, maybe 10 seconds here. Do I actually want to look at a 4-second window, a 5-second window, or a 6-second window? That's not just because I want to split this data up, but also maybe my ML algorithm can't wait for 10 seconds before it does something. It needs to have a lower latency to return. Then if I slice my data up, what is the window step that I need to do? Do I actually need if this is data at like 44 kilohertz, which could very well be, do I actually need that full resolution, or can I actually downsample to 8 kilohertz and just add a lot more performance to my device? And does that have an effect on accuracy? I don't know. Then from there, this is actually the same the same audio sample, but thrown through 4 different ways of actually creating a spectrogram. Which one of these spectrograms is the right spectrogram for me to feed into my neural network? And then all of these have parameters as well, right? How many bands do I want? What's the kind of the time scale? What is the FFT length that I want to do? So endless configuration options. I think if you multiple up them, like a typical audio model might have 100,000 different options that are, is one better, yes or no? We don't really know. And all of these have an impact as well on the target that you need to run it at. So here on the left, I have a spectrogram that is operating on this titmouse sample, and you see nicely kind of 4 tweets here happening. If I use an FFT length of 128, so I have 128 frequency bands, kind of the horizontal, the number of lines in horizontal layer, set it to 128. It costs me about 77 milliseconds to process on, the processor that I'm targeting. I think Cortex M4. If I want finer grained resolution, I can say, well, I want to set it to 256 bands. So you see, actually, there's more detail in these chirps, and that's something that the neural network can pick up. But that also increased my processing time to 159 milliseconds. Is that worth it? Is the actual increase in accuracy enough for me to actually pay that 80 milliseconds per inference penalty? Maybe it's not even possible because my device needs to do much more other stuff. Or maybe I don't hit my power consumption targets if I do it like that. So a lot of really interesting constraints that we have when designing that. So we started thinking, okay, what can we do here to automate this process and bring kind of this AutoML magic of like finding the hyperparameters in a neural network to this whole flow. So for that, we have built the EON Tuner. So EON Tuner is a new thing in Edge Impulse. Our ambassadors, that's a select group of people, will have access to this from next week, and the rest of the world well, a little bit later, depending on what our ambassadors find. But it's a AutoML pipeline. It's a way of actually evaluating all of these potential model architectures, dropping stuff where we think, okay, we're not going to get a result, and then presenting that in a nice and easy way straight for you. So you can actually make an informed decision on what the right architecture is. So some stuff that it does, so it is really made for sensor data. So don't expect to throw in, bank records or something and then find a model there. No, it finds the best model for sensor data, where we actually mix in input blocks. So for input blocks, these parameters could be, do we need to downsample, yes or no? What is the window length that I need to look at? Signal processing blocks, what type of spectrogram do we need to use? Do we even need to use a spectrogram? Can I actually get some other signals from this data? And then ML blocks, and that could be neural networks, could be transfer learning blocks, or could be classic ML algorithms. We've had great success actually at doing anomaly detection using just k-means clustering rather than a neural network. A really key part here is that you specify your device constraints up front. I need to run this on a Cortex M4. I have 120 milliseconds budget to run one inference, and I have 20 kilobytes of RAM available, basically. And extensible with your own DSP and ML blocks. So if you're doing something with, I don't know, ECG analysis, you have like pads on someone's head and you want to know what sleep stage that person is in. Cool. You can bring in your own extract features from ECG signal block, say which parameters are actually available, and we can search that complete search space too, which I think is cool. And ML blocks as well. So we wrap around the Keras tuner for that. And you can plug stuff in here as well. So we try to make a guess based on the type of data that you have and some instructions, or we say, okay, well, we're going to evaluate A, B, and C. But if you say, well, I actually have a really good idea about novel architectures that I want to evaluate, we have an API, looks very similar to the way that you write code for Keras tuner, where you can plug all of these things in and it will run it automatically for you. If you watch the presentation I did at the TinyML Summit in February, you know this quote, but it was so awesome that I want to repeat it here. The biggest win that we had from an early customer that was trying this out earlier this year is actually, we found a DSP configuration that works so well that it just wrote the final conclusion stuff in a normal control loop because they didn't need the ML anymore. I think that's the biggest win, right? We're not in the business, you might think that because we're in the TinyML Summit, we're not in the business of selling ML, we're in the business of getting more insight in what's happening in the devices all around us. So if you can solve something with signal processing, then yeah, shit, I'll take it because that is actually explainable rather than having, a black box neural network sitting at the end of my algorithm. I do want to highlight it's still an engineering tool. So don't throw random data in and then random stuff will come out and you'll trust that. There's a lot of considerations. So we always ask you kind of what is the thing that you're actually working at? Because that limits the search space already for us. So these are 4 of the audio categories that we have. So continuous or speech, basically, what is happening, like yes, no, or hello world, or whatever keywords. Continuous speech for the emotions. Gender is a bit of there's not really a right way of saying that. We should remove this from here. Events, like, breaking glass, gunshot, audio analytics knows all around that. I saw some of them already on the call. And then, continuous audio as well. And we'll expand on this for all of our other categories and make this pluggable. And then we also show exactly what went into the algorithm. So here we actually have 2 models that the tuner found with very similar performance. But one actually takes about twice as long to run as the other one. And it's not that, the one that uses less time is actually better. It's just that we give you kind of this insight in every single one of these kind of parameters and how it affects every class that you're actually looking at and the performance, etc. So you can make this informed choice of what is actually the best thing for your specific algorithm. So ETA, I actually put this on a slide in February where we actually did an announcement on when it was going to live. I'm not going to do that anymore. It's going to be soon available for ambassadors, really, really soon. And hopefully if they don't find anything, this will be available for everyone for free at jimpulse.com. And yeah, I want to give it back to Evgeny. And
thank you, Jan, for giving us an update on the tool. I think it's quite actually useful tool for the community and for developers there. because I think you did outline and highlighted this kind of big problem. How do you structure data? How do you collect the data? It's going to be really not the black box in the future, but the data box is going to be defining the success of your projects, right? And I think looking at this from the data perspective is good. And I also appreciated your kind of, I think we're getting more and more signals from the community there. It's not like neural nets for everything. I mean, you really need to look at the problem holistically and see what kind of approach to use for your problem. It could be a random forest or any kind of other classical algorithm, because people spend like hundreds of years, not hundreds, but many years developing these classical techniques, and they've been optimized really, really well. So no reason to ignore them. It does. Yeah.
The one thing that I would love, the thing that we talk with customers very often is saying, well, don't think of it as an ML problem. Think of it as a data-driven engineering problem. Yeah. And we could rename the conference to the Tiny Data-Driven Engineering Summit, but it doesn't wroll off the tongue as nicely as TinyML. But that's in essence what it is. Where do you get the data from? And then from there, kind of the rest of the algorithms follow relatively naturally.
So at the end of the day, it's still machine intelligence, right? That helps us to augment whatever we do.
Absolutely.
Whatever we call it. But thank you, Jan.
Of course, I do want to thank all our sponsors. So the premier sponsor, Newton, with their automated TinyML solutions. Executive sponsors, ARM, and we organized also a very nice panel that we witnessed just now. Edge Impulse as well. Jan was there and presented some of their work just now as well. Then also Qualcomm, working on advancing AI research to make efficient AI ubiquitous. Sentient, working on chip solutions to do ultra low power, high performance, deep neural network processors. Then our platinum sponsors, Infineon, we've had a keynote from Wolfgang from Infineon earlier today. Reality AI, working on advanced sensing with Edge AI and TinyML. Then our gold sponsors, Latent AI, working on adaptive AI for the intelligent edge. SensiML, building smart IoT sensor devices from data. And then our silver sponsors, EMSA, where Ilat also presented today what they are up to, Green Waves Technologies, HOTG, Imagimop, Kisho, Seed, and ST. And with that, that's the wrap for today. Thank you everyone for your attention and your attendance.